our topic is Fourier series. Fourier series, in this process, in network analysis subject, we try to study Fourier series analysis. In this case, any periodic function or any function can be represented by a set of DC component plus a infinite set of sinusoidal and cosinusoidal function. This representation is called as a Fourier series representation. Now, if you have any function, that function is represented here like f of t, this kind of f of t, and if this function f of t is equals to f of t plus minus n into t, capital T, where n is any positive integer value, where the capital T representing the constant term, which is called the time period of that function f of t, then this function can be represented into Fourier series representation. Okay, if the function is periodic in nature, that can be judged by this condition. If the function satisfies this thing, where the f of t equals to f of t plus minus n into t, then that function can be represented as a Fourier series representation. But if the function is not periodic in nature, for that case we will assume that function having the time period which is infinite, and for that case we try to represent that function in terms of Fourier transform. Okay, if the function is not periodic in nature, that is known as non-periodic, and for that we need to represent Fourier transform. So lower one, this function, the pictorial representation, this waveform that represent a periodic signal where the time period of that function is capital T. So after t time, this function is repeating itself, so it is having the time period of t, and after each t time this function is repeating. So for this case we can represent that function a set of DC component as well as sinusoidal and cosinusoidal representation. Okay, similarly, according to the previous picture also, here this is different waveforms are there, where this first one, this waveform is periodic square wave representation, where the time period of that square signal is this. This is the time period of the square signal. Okay, this one also another time period of that square signal. So this function is periodic in nature. Similarly, the bottom one, green one, that is the triangular wave, that is also periodic in nature. Okay, this function is not usual function, not sinusoidal, not triangular, not square, but different kind of waveform, but still it is also a periodic signal having a time period of capital T. So all these kind of waveforms which are periodic in nature, they can be represented as a Fourier series representation. So suppose we have a function f of t, that function must satisfy certain terms and conditions so that we can apply on them the Fourier series. Those conditions are represented by a Dirichlet condition. Those conditions need to be satisfied, then only we can apply Fourier series of that function f of t. First condition is the singular value function. The function f of t must be a singular value function. If it a singular value function, then there we can apply the representation of Fourier series representation having the finite number of value. Second, its integration must have the finite value, so that if we integrate we get non-infinite any term. Okay, so it must have certain specific value. Similarly, third point is it must have the finite number of discontinuity. Suppose this is, if a function is there f of t, this function, if the waveform of that function is suppose this kind of this kind of triangular wave, this kind of shortcut waves are there. So for that function, this portion, the function is available, certain values are there, but this period of time, this to this period of time, the function value is 0. Similarly, from this period to this period, again the value of the function is again 0. So during this period, we don't have any value of that particular function. So in this portion, we are saying that is discontinuous. This function may be discontinuous. Okay, this kind of discontinuity number must be a finite value for any function. Then there we can apply Fourier series. Okay. Similarly, the fourth point is it must have, f of t must have the finite number of maximum as well as finite number of minimum value. So what is that? Suppose we are having a function like this. This is a sinusoidal kind of waveform. Okay, and for that sinusoidal waveform, this is the maximum value. This is the maximum value. Again, this is the maximum value. So, as well as this is the minimum value. This is also the minimum value. So, 2 minimum values are there and 3 maximum values are there. So, if a function having the finite number of maximum value as well as finite number of minimum value, and if it is countable, then on those cases we can apply Fourier series. Okay, so if any function is there that is periodic in nature, that is singular value function, that is integrable, having a finite value, that must have the finite number of discontinuity as well as finite number of maximum and minimum value, then on those cases we can apply Fourier series. Okay, now if we apply Fourier series, the function can be a voltage signal, can be a current signal, can be a power signal, it can be any kind of logical signal. Okay, it must satisfy, again I am repeating, this must satisfy this condition, then only we can apply Fourier series. Okay, other than that we cannot apply Fourier series. What is that Fourier series? Again, that Fourier series f of t can be represented, that function of Fourier f of t can be represented a0 plus a summation of set of cosine function having a a1 cos 1 omega t, a2 cos 2 omega t, like that, an cos n omega t, where n can be 1 to infinite. Similarly, it is also a combination of bn b1 sin 1 omega t, b2 sin 2 omega t, b3 sin 3 omega c, like that, bn sin n omega t, where all the cases n can be up to infinite. So combine these functions, we can represent the function f of t, that function that is like a0 by 2, that is the DC component, like this, can be like this DC component. Then all these are the cosine function, all these are the cosine function. Okay, and we know the cosine functions are even function, so these are the all set of even function. Then third one, all sine function, these are all set of odd function, sine function is an odd function. So we can say the Fourier series is a combination of DC signal, a set of even function with its different harmonics, or we can say the cosine function having different harmonics component. Similarly, a set of odd function or a set of sine function with its different harmonics component. So in total, that is the representation of Fourier series of any function f of t, and if it satisfies all these Dirichlet condition and the periodic signal is nature, then we can represent that function f of t into Fourier series representation. Okay, now if we assume in this particular case that omega we know omega equals to 2 into pi into f. Okay, where the f is equals to 1 by t, so we can write omega equals to 2 pi by t. So by using that value of omega t, we can also represent that from here. We can write that same. This term, we are modifying this term. Instead of omega, we are representing that 2 pi by capital T, and after that in T. Similarly here also, instead of omega, we are putting that 2 pi by capital T. So again, Fourier series representation can again be present in this kind of form, where we are removing the omega or angular frequency into the time domain representation, that is 2 pi by t. Suppose this kind of case, different kind of waveforms are there, different types of waveforms are there. In this case, we are having 3 different colored waveform. Red color waveform, that is a sinusoidal waveform starting from this point to that point. So that is the time period of that sinusoidal waveform. It is starting from 0th time to pi, 2 pi. So that is overall the time period of this red colored waveform time period. Whereas if you go for the second one, blue color waveform, that waveform is starting from this particular point, and it completes its one particular cycle here. Okay, this point it completes one cycle, and after this to again this it completes its second cycle. So red waveform, it is represented, that red waveform, by this representation sin theta. So within this 2 pi time zone, blue color waveform completes its 2 cycle. So that means it's within that time zone, it is having 2 cycle. So its time period is half. That means its frequency will be double. So the representation of that blue color waveform is sin 2 theta with respect to theta, because it is having double half of the time period. So it is having double frequency, as frequency and time periods are reciprocal to each other. So the sin theta with respect to that, this signal can be represented as a sin 2 theta, having double frequency. Similarly, if you go for the green color waveform, its time period completes within that 2 pi time zone or angular domain, 3 particular cycle. Starting from this point, it completes its one cycle here. Then starting from this point, it completes its second cycle here. Again, starting from this point, it completes its cycle, third cycle here. So within that same time zone, it's complete 3 cycle. So its time period is 1/3 of the red one. So its frequency will be 3 times with respect to the red one. So if we consider the theta as the first one case, so the green color waveform having the frequency with respect to the previous one 3 times. Okay, so it is represented as 3 theta. In this case, we are saying this is the fundamental frequency or the first harmonics. This one the second harmonics, because it is 2 times, then the previous one, and this one the 3 times or the third harmonics. Okay, so this way we can say the different harmonics component representation pictorially and realize that.